Harder integration involving inverse trigonometric functions. So before we get started with some harder ones, let's just have a quick recap on some of the stuff we're going to need, just our basics. So what we're going to need the integral of 1 over the square root of a squared minus x squared dx. That's just going to equal the inverse sine of x over a plus a constant. And very similarly, the only difference being the negative 1 over the square root of a squared minus x squared dx is going to be the inverse cos of x over a plus a constant. Then we're going to have the integral of a over a squared plus x squared dx is going to be the inverse tan of x over a plus a constant. You might also see this one with 1 over a squared plus x squared, but that means you'd have 1 over a in the front here if that was the case, but we're going to write them like that. And yeah, we're going to use these to do some harder integrations that are going to result into inverse trig functions. First one we're going to look at, the integral of dx over x plus 2 squared plus 9. Now, looking at this, hopefully you can recognize that you've got something squared plus a perfect square, and it kind of looks like this one down here, because there's no square root, so we know these are probably not going to help, but it does kind of look like this one here, and we're going to go with that to help us. But we don't just have x squared, we have got x plus 2 squared, so we're just going to use a substitution, and it would make sense to let u equal to x plus 2. So this means that du dx actually just equals 1, so dx is just going to equal du. So using this substitutions, we're going to have the integral of dx, which we know is du now, over x plus 2, we let equal to u, so we just got u squared plus 9. And it looks pretty similar now to this one. The only difference is that we need a in the numerator if we have a squared in the denominator. So our a squared is 9, which means our a needs to be 3. So we need a 3 in the numerator. We can easily multiply by a factor of 3 as long as we then divide by a factor of 3 outside the integral. And this is now in the correct form where we can apply the integral. So we're just going to get a third of the inverse tan of u over a. A is equal to 3 plus a constant, but now we just need to put everything back in terms of x, and u equals x plus 2. So we know the final answer here is going to be a third of the inverse tan of x plus 2 all over 3 plus a constant. All right, let's look at another example. Just scrap all of this. All right, let's look at the integral of dx over the square root of 2x minus x squared. Now, this time we do have a square root in the denominator, which leads us to probably thinking it should be one of these two, either an inverse sine or inverse cos. At this point it doesn't matter, but something different we have here is both of these are in terms of x, and only in both of these, only one of the terms should be in terms of x, the x squared term. So this shouldn't be in terms of x. So if you have a situation like this, what you need to do is actually complete the square. And that's what we're going to do. So we're going to have the integral dx over the square root. And because our x squared term is negative. It's not really fun dealing with negative x squareds when completing the square, so we'll factor out the negative. And we have x squared, then we're going to have minus 2x. Now to complete the square, we need to add on half of the coefficient of x squared. So that's half of minus 2 is minus 1, and minus 1 squared is 1. So this completes the square, but we can't just change the question here. So what we're going to do, so what we've done, we've added on this extra 1, but it's inside this negative here. So when this negative gets expanded, we've got an extra minus 1 we've added down here. So to cancel it out, we need to add 1. So what we can do is just close this off and add 1 here. Because, again, expanding this out, we're just going to get minus 1, and then if we add 1, we haven't changed the question. But now we have a perfect square inside this bracket, and we can factorize it. So we're going to get the integral of dx over the square root of minus, this is just going to be x minus 1 all squared. And we're going to have the plus 1 on the end there. We might just change the order of that denominator. So we're going to get dx over the square root of 1 minus x minus 1 squared. And hopefully you can see that it is looking very similar to this one now, where we have 1 over the square root of a squared minus some x term squared. And just to make things easier, we'll make a substitution. So we'll let u equal to x minus 1, which means we're going to just get du equaling dx. So making that substitution, we're going to have the integral of du over the square root of 1 minus u squared. And you can see it's looking very much like this here, where a is equal to 1, because this is the a squared term. Square rooting 1 just gives us 1. So this is going to equal the inverse sine of u over 1, which is just u, plus a constant, and we know u is equal to x minus 1, because we'll put it in everything back in terms of x, and that's our answer for the integral. We're going to have a look at one more question, and this is the integral of the square root of a squared minus x squared dx. Now, this one's not directly doesn't look directly like an inverse trig fraction because there is no fraction, but this is going to result in some inverse trig functions. And to do this, we're going to need to use a bit of a trick. So if you ever get any in the form of the integral of the square root of some perfect square minus x squared or some variable squared, the trick you're going to have to use here is to let x equal either a sine theta or x equal to a cos theta. They'll both get the same result. We're going to use x equals a sine theta, but it really doesn't matter. And this is a strange substitution somewhat because we're actually letting x equal something as opposed to letting u equal something in terms of x. But the reason this is going to involve inverse trig substitutions is because you can imagine that, for example, with this one here, cos theta actually equals x over a, and you could rewrite this as theta equaling the inverse cos of x over a. So you could It's just easy to write letting x equal a cos theta instead of letting theta equal the inverse cos of x over a. But technically this is the substitution we're making. But we're going to use x equals a sine theta. So let's derive it. So we're going to have dx d theta. Derivative of sine is just cos, so we're going to have a cos theta. And we'll make dx the subject, so dx equaling a cos theta d theta. And yeah, let's go ahead and make some substitutions. So we're going to have the integral of the square root of a squared minus x, which we let equal to a sine theta, and dx, which is a cos theta d theta. So we need to tidy this up first. So we're going to have the integral of a squared minus a squared sine squared theta times a cos theta d theta. We can factorize out the a squared inside the square root. So we get a squared outside of 1 minus sine squared theta times a cos theta d theta. We're going to have the integral of the square root of a squared. Now 1 minus sine squared, that's just cos squared. Times a cos theta d theta. Now the square root of a squared cos squared theta is just going to be a cos theta times a cos theta d theta. Then we're going to have the integral of a times a, which is a squared. Cos theta times cos theta is cos squared theta d theta. We can take the a squared outside the integral because it's a constant, because we're integrating with respect to theta. So we're just going to have a squared outside of the integral of cos squared theta d theta. And that's something we do know how to integrate, because we should know that cos squared theta equals a half outside of 1 plus cos 2 theta. So we're going to make that substitution. So it's just using our double angle result. So we're going to have the integral of a half outside of 1 plus cos 2 theta d theta. We can take the half outside, so we're going to get a squared over 2 times the integral of 1 plus cos 2 theta d theta. So we can go ahead and integrate now. So we're going to have a squared on 2 all times integral of 1 with respect to theta is theta. And the integral of cos is just going to be sine, but we have to divide by the derivative of the function inside, and this function of 2 theta, derivative of that is just 2, so we're going to have a half of sine 2 theta plus a constant. But we're not quite finished here, because the original question was in terms of x, but ours is in terms of theta. So we need to fix that up. Now, in order to fix it up, what we're going to do, we're actually going to draw a triangle, because our original substitution of x equaling a sine theta, we could rearrange into sine theta equals x over a. And in our triangle, that's just our opposite over hypotenuse. So if we call this angle theta, our opposite side x, and our hypotenuse a would help us get would help us get our remaining side, which would be the square root of a squared minus x squared. And this is going to help us out in a second. So again, we're just going to tidy this up. We're going to have a squared on 2 outside of theta plus a half times sine 2 theta. We use our double angle results to turn that into 2 sine theta cos theta plus a constant. So the reason for making that triangle was so we can get an expression for cos theta, because we need it here. So doing that, we can get our expression for cos theta being our adjacent side, which is the square root of a squared minus x squared over the hypotenuse, which is a. And we can also get an expression, we need an expression for just theta on its own because we have this theta term. We can use this over here. So using this, we can just say that theta equals the inverse sine of x over a. And now we should have everything we need to put everything back in terms of x. So we're going to get a squared on 2, all outside of theta, which we know is the inverse sine of x over a. The half and the 2 will cancel. Sine theta is x over a. Cos theta is the square root of a squared minus x squared all over a plus a constant. And we can tidy this up. Maybe we'll expand everything. So we'll have a squared on 2, inverse sine of x over a. Over here, inside, we get a squared in the denominator, which will cancel out with this a squared in this numerator. So we get plus x root a squared minus x squared all over 2 plus our constant for our final answer.